Hello, I am Somnath Dasgupta. I teach at Jamia Millia Islamia, New Delhi. In this module, we will talk about the metamorphism of pelitic rocks. But before we go there, I have to give you an introduction starting from the concept of metamorphic fasces. As you know, pressure and temperature are the most important variables of metamorphism. However, metamorphic mineral assemblages are very strongly controlled by the bulk composition, that is to say the composition of the protolith. For this purpose, actually Escola defined the concept of metamorphism nearly 180 years before. A metamorphic fasces is defined as a set of metamorphic mineral assemblages repeatedly occurring in space and time, so that there is a predictable correlation between chemical composition and mineral composition. So, Escola identified that bulk composition plays a pivotal role in deciding about the nature of mineral assemblages in metamorphic rocks. Now, we have several metamorphic fasces which are diagrammatically shown in PT space in figure 1. So, in figure 1 you will see a rough disposition of the different metamorphic fasces in PT space, and in light blue lines I have drawn the metamorphic fasces series as well, where you can see that the line A represents the high pressure fasces series, line B the medium pressure fasces series, and line C is the low pressure fasces series. From this figure it becomes very clear that the series of metamorphic fasces developed in rocks will be quite different if the metamorphic field gradients are different. This is something that you need to keep in mind while interpreting the natural occurrences in the field before coming to any conclusion about pressure temperature domain of metamorphism. In 1960s, a dramatic development in metamorphic petrology saw the incoming of the concept of metamorphic fasces series. This was done by Miyashiro in his landmark work. Metamorphic fasces series is defined as a series of metamorphic fasces in a particular metamorphic terrain. Now, why is it necessary to distinguish different metamorphic terrains? This is because that each metamorphic terrain has a characteristic ambient metamorphic field gradient, which varies from one terrain to another. And the series of metamorphic fasces developed in a terrain is a function of the ambient field gradient. Miyashiro identified broadly 3 different types of metamorphic fasces series, which he called low pressure, medium pressure and high pressure fasces series. Now, we will see that the nature of metamorphic fasces varies in different metamorphic fasces series, and as a result the metamorphic mineral assemblages also vary in different fasces series. This is a big complications. Now, another point that you must remember before I start discussing about metamorphism of pelitic rocks, that we will talk about mineral transformations during metamorphism. How does transformation occur? They occur in response to simple chemical reactions. So, the controlling factors of a chemical reaction will be applicable to metamorphism as well. Metamorphic mineral reactions are basically of 2 types. The one is a solid transformation, which constitutes only 5% of metamorphic reactions, and the rest of the 95% metamorphic reactions are actually involving a fluid phase. So, they are solid fluid equilibria. With these few words as an introduction, we are now going into the metamorphism of pelitic rocks per se. So, now coming to the pelitic rocks proper. What are pelitic rocks? Pelitic rocks were originally shell or siltstone type sedimentary rocks, and they contain minerals like quartz, feldspar, lot of white mica and lot of clay minerals. Chemically, the composition can be expressed in the system Kf mash, so to say K2O, FeO, MgO, Al2O3, SiO2, H2O. Now, within this system, the pelitic rocks vary widely in composition, but all are characterized by very high Al2O3, SiO2 and K2O, variable FeO and MgO, but invariably low CaO. Very broadly speaking, pelitic rocks can be divided into two compositional groups. One is called low alumina pellite and the other a high alumina pellite. In a typical AFM diagram, low alumina pellite will be plotted below the garnet chloride tie line, and the high alumina pellite will be plotted above the garnet chloride tie line. Now, in figure 14.3, I have shown you a typical phase diagram in the system Kf mash, where all the possible mineral reactions are plotted. As you can see, with increasing pressure and temperature, one will encounter a sequence of reactions, but the nature of mineral reactions will be different along the PT gradients shown as blue arrows, the three metamorphic field gradients of Miyashiro. You can see that rocks metamorphosed under medium pressure fascist series will not experience the same kind of mineral reactions as those in the low pressure fascist series. This is the uniqueness of the concept of metamorphic fascist series. Given in this background, let us now discuss the most well studied metamorphism of pelitic rocks along the medium pressure fascist series, which is also known as Barovian metamorphism. Now, why Barovian? The reason is Barrow first documented it from Scotland way back in early 1900. So, after such a long time, still the observations of Barrow are valid, and which Barrow showed that in Scotland, with progressive metamorphism, different mineral zones are developed, starting from the chloride zone at the lowest PT, followed by respectively biotite zone, garnet zone, staurolite zone, kyanite zone and selemonite zone at the highest PT. Now, in the chloride zone, pelitic rocks contain chlorite, white mica, muscovite, potash feldspar and quartz mainly. In the biotite zone, chlorite, potash feldspar, they react to produce biotite. So, biotite makes its appearance in the biotite zone in pelitic rocks. Both the chloride zone and biotite zone fall within the green schist fascists of Escola. At the beginning of the amphibolite fascists, we have the garnet zone in the Barovian zonal sequence, where the low alumina pellite will develop garnet. Garnet appears through breakdown of chlorite and muscovite. And you must note here that a very special type of garnet called spessartine garnet, which is manganese rich, can develop in the biotite zone given the original high manganese content in the bulk composition, but otherwise normal iron, magnesium, garnet will make its appearance in the garnet zone. In the high alumina pellite, on the other hand, we will not see garnet, but we will see chloritoid. This is followed by the staurolite zone. In the staurolite zone, in the high alumina pellite, we get chloritoid breaking down to staurolite, and staurolite makes its appearance in the low alumina pellite also from the breakdown of chlorite and muscovite, and also partially from the breakdown of garnet. By this time, we have reached a temperature of around 550 degrees Celsius and 5 to 6 kilobar. At the subsequent higher metamorphic zone, that is the kyanite zone, the staurolite starts to break down to produce kyanite in both low alumina pellite and high alumina pellite. Kyanite, being an aluminous mineral, will be more abundant in a high aluminous pellite, but the distinction between low alumina pellite and high alumina pellite becomes fuzzy at this grade of metamorphism. The kyanite zone is reached at around 600 degrees Celsius and 6 to 6.5 kilobars. After the kyanite zone comes the sillimanite zone, approximately at 650 degrees Celsius and 6 or 6.5 kilobars. Here, kyanite can be partially changed into sillimanite by the polymorphic transformation kyanite to sillimanite, or else sillimanite will appear from the breakdown of the rest of the staurolite which were preserved till then. Following the sillimanite muscovite zone, we have a zone which is called sillimanite potash feldspar. The sillimanite potash feldspar isograd is characterized by the breakdown of muscovite. So, we are no longer getting muscovite in the rock. Muscovite breaks down to potash feldspar plus sillimanite plus water in the presence of quartz. So, now you see that potash feldspar was present in the chloride zone, but nowhere in the biotite, garnet, staurolite, kyanite and normal sillimanite zone. But now at this condition, potash feldspar makes a reappearance in the pelitic rocks, and we are bordering into the granulite fascists at this stage. Now, suppose I increase the temperature further, then what happens? Now, the pelitic rocks become partially molten. And what are the minerals they melt? These are both muscovite and then biotite. Muscovite melts first, followed by biotite. But we distinguish two types of melting reactions which are described, which are shown in figure 14.8. The first stage, we have a fluid present melting, and in the second stage we have a fluid absent melting. So, summarizing, both muscovite and biotite melt, but first muscovite and secondly biotite, and first melting is in the presence of fluid, and in the second case it is in the absence of fluid. The melt produced in amount is much more during biotite melting. More than 20% of the rock can be partially molten, but in case of muscovite melting, only 5 to 10% of melt can be generated. Now, partial melting has a different name also, a nomenclature. This is called anatexis. Anatexis means partial melting, and pelitic rocks, when partially molten due to the process of anatexis, produce a rock which is called migmatite. You can see a photograph of a migmatite in figure 14.7, where you can see that the rock is a composite rock containing light layers The light layers are of granitic composition, and dark layers which are called melanosomes, which contain mainly the ferromagnesian minerals. You can easily notice a lot of garnet in those melanosomes. The light layers are called leucosomes. So, at this stage, well within the granulite fasces, what do we have in a pelitic rock? We have quartz, plagioclase feldspar, potash feldspar, sillimanite, garnet, with or without biotite. In India, we often call this rock as condylite. You might have heard about this rock, condylite. This is a granulite fascist metapelitic rock. We can still raise the temperature, but that will be the subject of another module where we will talk about metamorphism under extreme conditions. Now, let us look at what happens when we metamorphose a pelitic rock in the low pressure fascist series. Or this fascist series has got different names. Some people call it Abukoma type fascist series, some people call it Bukhan type fascist series. Whatever may be the name, the important point to note is that kyanite, garnet and staurolite, all the common minerals in the Barovian fascist series we discussed just before, they do not appear in Bukhan type or Abukoma type or low pressure fascist series. Instead, what do we get? We get andalusite at lower temperature of the aluminosilicate polymorph, which changes to sillimanite at higher temperatures, and you can have lot of cordierite under such circumstances. Then we look at the high pressure fascist series metamorphism. Now, the names of the fasces are even different. We start with geolite fasces, changes to prehnite, pumpelliite fasces, followed by blue schist fasces, and then finally to eclogite fasces. The pelitic rocks in the blue schist fasces contain the minerals talc and phengite. Now, these minerals are both colorless, as a result of which the rock is colorless and we call it white schist. It is completely different from the green schists that you must have come across. So, white schists appear in the blue schist fasces metamorphosed pelitic rocks. In the eclogite fasces, lot of changes occur in the pelitic rocks. Magnesium rich garnet and kyanite and rutile are the major minerals there along with quartz. But in eclogite, we do not have plagioclase. Plagioclase decomposes at the boundary of the eclogite, producing different minerals. We will further explore this kind of metamorphism in a separate module. So, what did we observe during the last few minutes? We learned that metamorphism has got a very important variable in addition to pressure and temperature, that is the bulk composition. We also learned that metamorphic field gradient represented by metamorphic fascist series will decide what will be the series of metamorphic fasces in a terrain, or in other words, what will be the series of minerals developed in pelitic rocks in different terrains. They can be quite different depending on the same difference of metamorphic field gradient. So, what happens? We are handling a very complicated situation: pressure, temperature, bulk composition, metamorphic field gradient, all interplay with each other to produce the diverse metamorphic mineral assemblages that we observe in pelitic rocks. You need to be really careful to do that. In this recent years, we are using more of pseudosections rather than phase diagrams to understand the stability fields of mineral assemblages in pelitic rocks, which I have given some figures in the text 14.6 and 14.9, where pseudosections are represented. You can look at the pseudosections. What is a pseudosection? A pseudosection is a phase diagram for a particular bulk composition, so to say for a particular rock, and should be applicable strictly for this particular rock only. But if you look at the pseudosections carefully, you will see that the sequence of mineral reactions are very, as I discussed in this presentation, are very beautifully developed in figure 14.6, and even in 14.9 you can see the melting reactions which I have discussed earlier while talking about muscovite and biotite melting. So, these pseudosections help us in a great way to understand the pressure temperature stability limits of the different mineral assemblages. Here I have shown you in pelitic system, but the similar phase diagrams can be shown in other rock types as well. So, in summary, what did we learn today in this presentation? We learned that metamorphism can be a really complicated process. For example, the general two important variables like pressure and temperature are not sufficient to understand the evolution of metamorphic rocks. You need to take into consideration the bulk composition, you need to take into consideration the metamorphic field gradient in a particular terrain. As you will see that the nature of mineral reactions and the nature of mineral assemblages produced in the Barovian fascist series is not the same as that produced in the high pressure fascist series. So, taking all these things into consideration, we have to understand the metamorphism of pelitic rocks in totality. And we have seen that although broadly speaking the concept of Barrow that was promulgated from the study of Scottish rocks is applicable over a large areas in the world, and in India we also describe Barovian type fascist series from the Himalayas. So, and some other scientists also inferred about the Barovian fascist series in Singhbum mobile belt as well. So, metamorphism of pelitic rocks is really a complicated situation. You need to look at the rock, you need to look at its composition, you need to understand the terrain so that you can get a holistic picture. I hope that this was helpful. Thank you very much.